telescoping series. We're going to jump right into an example. We want to determine if the series converges or diverges by finding S sub n, the formula for the nth partial sum, and evaluating the limit as n approaches infinity of S sub n. So we don't typically do this. It can be kind of difficult to find a formula for the nth partial sum, except in the case of a telescoping series. So our series is the sum of n equals 1 to infinity of 4 over the square root of n minus 4 over the square root of the quantity n plus 1. Let's go ahead and start to write out a few of the terms in this series. So we're going to go ahead and substitute 1 into each n to get our first term. So we're going to have 4 over the square root of 1 minus 4 over the square root of 1 plus 1, which is 2. And this is a sub 1. Then we'll substitute in 2. So 4 over the square root of 2 minus 4 over the square root of 2 plus 1. So the square root of 3. This is a sub 2. And then we'll substitute in 3 next. So we're going to have 4 over the square root of 3 minus 4 over the square root of 3 plus 1. So over the square root of 4. So this is a sub 3. And I'm not even bothering to simplify any of the square roots here, because what I really want to do is identify the pattern. What we've done here is written out S sub 3. We're adding the first 3 terms of the series. But something nice happens. So negative 4 over the square root of 2 plus 4 over the square root of 2 are opposites, and they add to 0. So these cancel out. And negative 4 over the square root of 3 plus 4 over the square root of 3 are also going to cancel out. So for S sub 3, that partial sum is equal to the first part of the first term and then just the last part of the last term. All of the middle terms collapse, which is why we call this a telescoping series. Because if we think about a telescope, which opens up really long to look at the sky and then collapses down really nicely to pack and put away. So these middle terms collapse down. And it doesn't just happen for the first 3 terms. Let's go ahead and add on one more term here. Let's look at a sub 4. So 4 over the square root of 4 minus 4 over the square root of 5. This is the a sub 4th term. So if I go ahead and think about now S sub 4, adding the first 4 terms together, now again, those adjacent terms are going to cancel, and all that's left is the first part of the first term and the last part of the last term. So we write out enough terms until we can find the general pattern. And now we're going to find a formula for S sub n, not just S sub 3 or S sub 4, S sub n. So let's go ahead and sort of erase this here. So we're going to say plus dot 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 plus. So all of these pieces in the middle are going to cancel. And let's write out what the general last term is going to be. It's going to be just this general a sub nth term that's right here. So we're going to put 4 over the square root of n minus 4 over the square root of n plus 1. This is the a sub nth term. And we know that all of these middle pieces, again, are going to collapse and cancel out. So the formula for S sub n, adding all of these terms up, is going to be just that very first part of the first term, 4 over the square root of 1, which is just 4. And then just this last term, minus 4 over the square root of n plus 1. So now this infinite series is equal to the limit as n approaches infinity of this nth partial sum formula, 4 minus 4 over the square root of n plus 1. And as n approaches infinity, the second term is going to go to 0. The top stays constant, the bottom's getting really big. This whole quantity is going to go to 0. So all that's left is 4, which is a finite number. So this infinite series converges, and more than that, it converges to 4. So that's really powerful. We can't always find what an infinite series converges to. We often just look for whether it converges or diverges, but if we find the formula for the nth partial sum, we can also find what it converges to. Let's summarize what we just found out about telescoping series. Informally, a telescoping series is one where, past a certain point, the terms cancel out and collapse on each other, and leave the infinite series to add to just a few terms at the beginning of the series and some general terms at the end. This is one of the few types of series we will determine convergence or divergence using the actual definition that the sum of n equals 1 to infinity of a sub n is equal to the limit as n approaches infinity of s sub n. Let's look at another example. Determine if the series converges or diverges. We have the sum of n equals 1 to infinity of natural log of the quantity n over n plus 2. This one doesn't exactly shout that it is telescoping. We're often looking for a series that has a difference, right? Two things being subtracted as part of the general term. But here, I don't have that exactly until I remember some log properties. So I can rewrite this as the sum of n equals 1 to infinity of natural log of n, the numerator, minus natural log of the denominator, n plus 2. So now I have this difference as the general term. So let's go ahead and start to substitute in our starting index and recognize that pattern. So here we're going to go ahead and have natural log of 1 minus natural log of 1 plus 2. So we're going to have natural log of 3 there. Plus, now we're going to substitute in 2 next. So we're going to have natural log of 2 minus natural log of 2 plus 2, which is natural log of 4. So just notice already we have a sub 1 and a sub 2, and the adjacent terms don't cancel out. So the last example was really nice because the adjacent terms canceled, but that's not quite happening here. But let's go ahead and keep going. So if we substitute in 3 next, we're going to have plus natural log of 3 minus natural log of 5. Okay, so I do start to see my first set of canceling terms. I have negative natural log of 3 as the second piece in the first term, and then plus natural log of 3, that's the first piece in the last term. So I do have some canceling that's going to happen. Let's go ahead and write out one more term. So if I substitute in 4, we're going to have plus natural log of 4 minus natural log of 6. So here what we have is we're adding the first 4 terms. So all of this is going to be s sub 4. And the pattern is the last part of the first term is canceling with the first part of the third term. So we kind of have to jump over one whole term in order to start recognizing when things cancel. So now in the second term, the last part, negative natural log 4, is going to cancel with the first part of the fourth term. So what is going to be left over? That's what we're trying to recognize. What's going to be left over? So we have natural log 1 and natural log 2 at the beginning of the series. And then at the very end of the series, we have 2 terms left over. So we have the last parts of the last 2 terms. So we want to use that to generalize s sub n. We're going to generically need the last term a sub n and the term before it a sub n minus 1. Natural log n minus natural log of the quantity n plus 2, that's the last term. So here's that last term over here, and then I need the term before it. So the term before it is the a sub n minus first term. So if I replace each n with n minus 1, that means that this term is going to be natural log of the quantity n minus 1, and then minus, if I replace this n with n minus 1 plus 2, well, negative 1 plus 2 is plus 1. So we're going to have natural log of n plus 1 plus, and then the a sub nth term. Okay, so now s sub n, the formula for s sub n, what we know that's left over is the last piece of the last term and the last piece of the second to the last term. Those are going to be the only pieces that are left over. So let's cross out everything else. So our S sub n formula is going to be natural log 1 plus natural log 2. Well, natural log 1 is 0. So S sub n is just going to be natural log 2 and then minus natural log of n plus 1 and then minus natural log of n plus 2. So we know that the original series, the sum of n equals 1 to infinity of natural log of n over n plus 2 is equal to the limit as n approaches infinity of natural log 2 minus natural log of the quantity n plus 1 minus natural log of the quantity n plus 2. Well, as n approaches infinity, natural log of n plus 1 and natural log of n plus 2, those are each going to infinity. So what we basically have is like natural log 2 minus infinity minus infinity. And so this is going to negative infinity. So I could think about this as kind of like adding the opposite. So negative infinity plus negative infinity, that's negative infinity, plus natural log 2. Well, that's still negative infinity. So here, this is negative infinity. So my infinite series diverges. Here were two examples of telescoping series, one that we showed converged and the other that we showed diverged.